everybody, this is a video for our Chapter 1 notes for Math 95. What I'm going to do in these videos is go through the notes with you, not necessarily do every single problem together, but go through most of them, and then if maybe there are 3 or 4 examples, I might do the first 1 or 2, and then let you check your work with the filled-in version as we go, okay? The screen recorder I'm using is a free version and it allows me to do 15 minutes at a time, so I'm going to do that. So there may be several videos for Chapter 1, but I will clearly label those. So depending on which class you are in and how many times I've seen you with this crazy first week, we may have gone over some of this first part. You can skip ahead if you feel like you've done it already, or you can listen through it again. So we're here talking about real numbers in Chapter 1. So real numbers are the set of numbers that basically include any number that you probably can think of. Okay, there are numbers that are considered not real numbers. They're called imaginary, and it's nothing that we'll talk about here in Math 95. I'll just mention in a few minutes what makes numbers imaginary versus real. But so we have all different kinds of numbers in the real numbers. We have negatives, fractions, decimals, the number pi, some square roots. All of those are different kinds of numbers that are in real numbers. And then we also make some sets of numbers that are part of these. Okay, so we take all of the numbers and real numbers and kind of split them up into little smaller categories that are more alike. Okay, so one example of a set of numbers that we have in the real numbers are called the natural numbers or the counting numbers. And so I always think about this counting part here, and I think about if we were teaching a young child to count, okay? We were going to count their teddy bears with them. We would not start counting at -8 or 53.7 or 2/3, right? We would start out counting their teddy bears with 1. And would move on to 2, 3, 4, going on forever. They might have 973 million teddy bears, but those are the kind of numbers we'd use. So those are what we call the natural numbers, just going from 1 and above, no fractions, no decimals. Then we move into another set of numbers that's called the whole numbers. And my little trick here is that whole has this O in it, and that's going to remind you that the whole numbers include the number 0. So it's 0, 1, 2, 3, 4. So it's those natural numbers plus just adding on 0 on there. And 0 is kind of a special and important mathematical concept for people to understand when mathematical ideas were being developed, because it's easy to think about how many sheep you have in your field or how many teddy bears you have, but then the idea of needing a concept for not having any is important. So when we look at these two sets, we can see that if we think about the natural or counting numbers, we have 1, 2, 3, etc. And then if we look at the whole numbers, it includes all of these natural numbers plus the number 0. So if we kind of think of this as being nested, right, the natural numbers are all included in the whole numbers. So think of it this way. Think about if we have a room full of dogs and someone says, well, there's a poodle. And I say, well, I thought these were all dogs. Well, it is, right? A poodle is a subset or a smaller group of dogs. Okay? And I can say also, well, those are all animals in that room. Well, that one living thing can be called a poodle and a dog and an animal, right? They're all kind of nested, and that's the same idea we have with these sets. Integers goes a step further. So it goes from -infinity, includes negative numbers and 0, and whole numbers. So it includes natural numbers in there. It also includes 0, so this whole set is the whole numbers, and it includes negatives also. So these are all the integers. Now notice it does not include any decimals or fractions yet. So here we have negative up to positive, and these are called the integers. So again, this could include -4 million, right? It just can't include -4 million.1. We don't have any decimals or fractions. So rational numbers here's where our decimals and fractions come in, okay? So if you think about the word ratio, if you remember what a ratio is, it's the comparison of two things. Like for example, you might say the ratio of students to teachers is 8 to 1. One way to write that is as a fraction, so it's kind of the same root word there. So rational numbers, we know they're rational if they can be written as a fraction. And just to be clear and thorough, I'm going to say it has to be a fraction made up of integers. So it could be 5 over 1 or negative 8 over 3. It can't be 4.2 over 5. Okay, it has to be integers. And as a decimal, if a rational number is written as a decimal, it has to either end, so it either ends or it repeats. Okay, so for example, some rational numbers, if they're fractions, could be 2/3 or negative 1/5 or 8 over 1. And if a decimal ends or repeats, it could be something like 1.375, or it could be 2.3 repeating, right? That line means that number repeats forever. So those are some examples of rational numbers. Now, rational numbers also include all of these, because if I have a number like 3, for example, that is also a rational number because it can be written as a fraction, 3 over 1. So any of these can be written as fractions, so that means they are all rational numbers. I'm going to scoot around my other writing here. So again, here are my rational numbers. All rational numbers are integers. All rational numbers are whole numbers. All integers are rational numbers. All whole numbers are rational numbers. All natural numbers are rational numbers. But there are also numbers in here, like 2/3, that are not any of these smaller sets. Okay, so irrational numbers, I'm just going to change colors here to kind of make it clear that there's a little bit of a divide here. So irrational numbers, when they are written as a decimal, they go on forever without repeating. Okay, so for example, I'm just going to make up one that could be to like 3.24761548825, going on forever, never repeating. Another example is the number pi. Okay, if you remember pi, we use that for dealing with circles. We often say it's 3.14, but that's just an approximation of it. And something else we'll talk about a little farther on also, but if we have the square root of something like 10, for example, if we take the square root of something that is not a perfect square, and we'll talk more about what those mean, then it's going to give us an irrational number. Okay, so no number could be a decimal that ends or repeats and also at the same time a decimal that doesn't end or repeat, right? So rational numbers and irrational numbers, there's no crossover there. And anything in the natural whole or integers would not make a decimal that goes on forever without repeating. So irrational numbers are their own little area over here. Okay, there's no crossover. So if a number is natural, it's also whole, it's also an integer, it's also a rational. If it's irrational, it's none of those. Okay, so it can never be rational and irrational, they're kind of separate. And then all of this together, didn't leave myself much room there, all of these together are going to be real numbers. Okay, so real numbers encompass all of these. So I said before I'd let you know about what imaginary numbers are. We don't have to worry about them in this class. You will talk about them if you go on to Math 120. But imaginary numbers basically have to have a negative under the square root sign. So for right now, we would say that you can't take a square root of a negative number. It doesn't exist in the real numbers. Imaginary numbers are another set. They deal with that. Don't worry about that at all. Okay. All right, so now here, down here, we're asked on this page to check which set or sets each of these numbers belong to. So I'll do the first couple, and then I'll pause it so you can do the rest. So 15.68, okay, think about counting numbers, remember, or natural numbers. They mean the same thing. Those are the ones you'd use to have someone count their teddy bears. I don't think you're going to start with 15.68, right? So we can say that that is not a counting number. We're not going to check it. It's not a whole number. It's also not an integer. Remember, these three never have a decimal or a fraction part. Now, the only difference would be if it's a fraction written as like 5 over 1, that really means 5, right? Or 10 over 2, if it reduces down to a whole number or a counting number, then yes, it is. But here it's 15.68, so we're not going to have any of these. That is a rational number because the decimal point ends. It can't ever be rational and irrational, but every number we deal with is going to be real, as long as it does not have a negative under the square root. Okay, let's look at the next one. Negative 37. Okay, well, again, we're not going to count negative 37 bears. We know that counting numbers start with 1, whole numbers start with 0. However, this is an integer. That is also a rational number. We could write it as negative 37 over 1. Can't be both rational and irrational. It's also a real number. So I'm going to attempt to pause this video for a second, and I will fill out the rest of the chart while I'm paused. You do the same, and then you can come back and check your answers. Okay, so hopefully you took some time to fill out this chart. You can also pause this video for a moment and see, compare your answers. So just quickly, this one is a decimal that goes on forever. That means it's rational. This is 0, so everything from whole up to rational. Radical 64, remember the square root of 64, and we'll remind ourselves about square roots in a minute, but if you take that in a calculator, or if you think this means what number times itself equals 64, I'm looking for this number, it's 8. So because it's just 8, it's going to be a counting number actually, right? This one is a decimal that never ends and never repeats. That's what I'm trying to represent here. That's going to be irrational, still real. 24 is a counting number. And then square root of 10, I want to know some number times itself that equals 10. Well, if I think about integers, 3 times 3 is 9, and 4 times 4 is 16. So when it's not a perfect square, like my example up here actually was 10 also, that means that if you put square root of 10 in your calculator, you're going to get 3.1, blah, 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 blah. It's going to go on forever without repeating. That is an irrational number. So a square root could be either 1, depending on whether the answer to it is an integer or an irrational number. Okay, so let's move on. Now with any of these, if you have questions, just kind of jot down where your questions are, and then you can ask me either in class or on office hours or anything. Okay. So since I am coming up to sort of the end of my time, my 15 minutes for this one video, I'm going to pause my video again. I'm going to kind of fill in these next few, and then I'll start it again just to go over them without spending the time actually writing while I'm talking. So I'll be right back. Okay, so I filled in these next couple boxes, and I just want to spend a minute here talking about them before finishing up this portion of the video. So when we're adding two negative numbers, a lot of people remember a negative and a negative is a positive. That's true when we multiply and divide. When we add two negatives, add up to a negative. Look at y here. If I have -4 and -3, imagine I have little chips that are negatives. So I have 4 of those chips and 3 of those chips. Little arrow, I put them together, I have 7 of those negative chips. Nothing became positive there. So when I am adding two negatives, I just want to add the number parts, and that's how many negatives in all. So you can see I did some work over here to see how many negatives in all. So the circled parts are my final answer. When I add a negative and a positive, it's a little different. My sign of my answer is whichever there are more of. So if I look at this first one here, -4 plus 9, I have 4 negatives and 9 positives. So what happens then is every time I have a negative and a positive put together, they cancel each other out. It's like going one step forward and one step back. So if I cancel out 4 negatives with 4 positives, then what I have left is 5 positives. That's what I have left there because there were more of them. So take a look at these other examples, see if you can figure out where I got the answers from, and we'll start there in the next video.